Okay, thank you very much. So it's a pleasure to be the last speaker of this nice program. Thanks to the organizers for organizing it. So the title is Perturbations and Projections. And as you all know, projections are a very sort of convenient tool in the study of representation theory. For instance, if you look at representations of finite groups, then the regular representation, which is a very simple representation, basically contains all the irreducible representation, all the finite dimensional irreducible representations of finite groups. So if you want to know anything about any finite dimensional irreducible representation, you can start with a simple representation and then look at the projectors inside this representation and then study all the representations. So they are very useful in this setup. For instance, if you look at the symmetric group, then that's a way to define all the representations, all the finite dimensional irreducible representations in the first place. So what I want to do in this talk is give you an idea how something like this also works in the setup of topological quantum field theories. So, of course, in this setup, the notion of projections is much more complicated. In fact, it's some kind of categorification of a projection. And also the notion of subrepresentation gets sort of much more interesting than in representation theory. So, there will be a preprint coming out about this in collaboration with my PhD student, Fabian Kloos. It will come out in the next few weeks, I hope. And before I start, I would like to sort of set the stage by introducing notations basically about two-dimensional topological quantum field theories, because I will study this here for this talk in two-dimensional setup. But I think it's very general, so it should be possible to apply this in any dimension. So 2D TQFTs. So what is a 2D TQFT? It's a functor, let's call it T, from the Bordism category Bord to 1 to the category of vector spaces, which basically associates to objects here, which are a bunch of disjoint circles. Let's take n of them. Associates the tensor product, respective tensor product of some vector space V, and to some Bordism. Let's take this one of these objects. It associates T of this, which is homomorphism in of V tensor to V, for instance. Okay? In physics terminology, this thing here is the space-time of your quantum field theory. And for this talk, it will be Euclidean, and this here is a correlation function. Okay, so in physics, there's more to these topological quantum field theories than is encoded in the structure. Namely, if you look at physical systems, something which is sort of rather intricate are so-called defect lines. So you can introduce in quantum field theories so-called defect lines. And what are defect lines? Well, they are basically irregularities in this quantum field theories which live on the space-time along lines. So I will look at defect lines. So if you have some space-time, so some surface basically with some boundary components like this, might have some genus, then you can introduce sort of irregularities in your quantum field theories along lines. So for instance, there could be a line going like this, or there could be a line which goes along the surface and hits sort of the boundaries of the surface. And also, these kind of defects can form junctions, and so you can have networks of these type of defect lines. Okay? So they are very interesting from a physical point of view. And to encode this in this kind of structure, you basically have to enrich these categories. What you will get in the end out of this is a sort of nice structure. Namely, you will find that your two-dimensional topological quantum field theories together with these defect lines form a two category. So. Okay, how is this built up? Well, the objects in these two categories are just all the possible functors of the unenriched categories here, so all possible 2D TQFTs. These are the objects. Then there are one morphisms between two objects, so more of T prime. So these two T and T prime are now two possibly different two-dimensional topological quantum field theories. And these morphisms are just the defects which connect possibly these two different quantum field theories. So if you look at sort of part of your space-time here, you might have some defect line here. I think I drew that red. So let's call it D. And on this side of the defect there, the quantum field theory is governed by the 2D TQFT T, and on the other side it's governed by T prime, and they could in principle be different. So if you look at the physical setup, I mean, one thing which one could study, for instance, are theories of electrons on some two-dimensional material, and this defect, for instance, could represent an interface where you just put together two different materials, right? And you could describe what happens to these electrons and get some quantum field theory out of it. So these these defect lines somehow can they can glue together basically two different TQFTs. Okay, these are the one morphisms of your theory. So what are the two morphisms? So if you now have two defects, let's call them D and D prime, which are morphisms between the same sets of topological quantum field theories, then the morphisms in this picture are just like this. So you have your defect here, and these are basically defects on defects, so they are point-like objects which you can sort of put on the defect like this. So, so you have a 2D TQFT T here, 2D TQFT T prime here. On top, you have your defect D. Let's put your defect D here, and this here is your defect D prime, and this here is a defect of defects, and this here is in here. This here is in homomorphisms of D and D prime. Okay? So if you look at these parts of your worldsheet, then you will notice that you can basically cut out a disk around this point here. So this space of homomorphisms basically is nothing but your TQFT functor. I call the whole TQFT functor together now Z. So this encodes all the possible T's here. And this space here is nothing but Z applied to the object now, which is just a circle with 2 points corresponding to these defects here. So the circle is labeled by D prime D and 2 series on both sides. Okay, so this is nothing but this space of homomorphisms. Okay, so if I told you what the objects are, the one morphisms, the two morphisms, so what are the compositions of these morphisms? So the one composition is I just sort of draw pictures like this. So you have two defect lines here, let's say D and D prime, and here you have your 2D theory T and T prime and T double prime. So D is a morphism between T and T prime. D prime is a morphism between T prime and T double prime. Now you have a topological quantum field theory. So what you can do is basically sort of slide things around. So you can just move these two things together, and what you end up with is a situation like this, where you now only have one defect in the middle. You have here theory T, here T double prime, and this defect which you get here is just the decomposition, the one decomposition of these two defects, and I sort of denote this by a tensor product. Okay, that's the one composition. So what about two composition? So in two composition you have three different defects now between two TQFTs. So you have T here, T prime here, and you have two of these objects, so defects on defects, here and here. Let's call this phi and psi, and then you have D here, D prime, D double prime. And again, you can, since this is topological, you can slide it together. So you bring these points together, and you end up with a situation like this, where now you have D, and there's just one defect on defects, which is then called phi composed with psi. So that's the two composition. Okay, so in this way you define out of this structure a two category. So all the TQFTs, all 2D TQFTs together form this two category. Okay, there are some more properties which I need. So for instance, in this two category, for every object there's some kind of identity one morphism. One morphism. So for all 2D TQFTs T, there exists what I call it T in the morphisms of T and T. And this is just the invisible defect. Which means basically you mark sort of a line here on the surface, but really nothing happens there. So these are always there in TQFTs. So you have identity one morphisms. And the other point I want to make is about so-called adjoints. So assume now that you have a defect D in morphisms from T to T prime. I draw it like this. So here is T, there is T prime, and this is defect D. Then there are adjoints, namely the right adjoint and the left adjoint of this defect, which are in morphisms of T prime T. And these satisfy the following conditions. Namely, if you look locally in the surface and you start with the defect D, then so here will be your defect D, here will be your defect D right adjoint, here will be D again, and you have maps like this. So this is the dotted lines will always be the invisible defect. So this will be the identity of T. This is the identity of T prime, and here these maps are so-called evaluation and co-evaluation maps. And the point here is that there are defects D prime and evaluation and co-evaluation maps such that this is always the same as this. Okay, and also the other way around. Where now here is D again, D, and this is D left adjoint, and there are respective evaluation and co-evaluation maps here. Okay, so I will assume that we have this kind of structure. In our situation, the situation we are dealing with, this is non-pivotal. This means that the right adjoint will not be the same as the left adjoint. So that makes things life a little bit more complicated.
So there also notion of extended to the TQFT when we replace this by top functor between two categories. So is this can this be incorporated? I mean, is this going to give some additional structure, or is it already kind of included?
I wouldn't say, well, I'm not sure what you mean by included. I mean, this is additional structure, but it's sort of tied to this 2D TQFTs. Like, I mean, yeah, I'm not sure what you mean, but for instance...
I mean, can I, in this two-category construction, can I understand TQFTs not as ordinary TQFTs, but extended TQFTs?
I think they're already fully extended. You can take one of your T's to be the empty theory, and then you've got boundary conditions.
Yes.
And so it's already there.
So the objects in this objects associated point would be these.
Yeah, it's morphism from
T
to
to empty.
the empty theory.
Okay. Okay, and another thing I want to mention is that if you look at these diagrams, right, which are somehow just parts of your surface where defects do something, then these diagrams are nothing but the string diagrams you get when you study 2D, when you study two categories, which you work. Okay. All right. So now I set the stage for what I want to tell you. So in physics, so this will be, in the beginning, I will try to say some words about some interesting physics, and then this will be sort of put in this framework, and then will be math. So in physics, often interesting quantum field theories are defined by means of perturbations of some simple quantum field theories. And often there's no really good way to understand these more interesting quantum field theories on their own. And these perturbations are often also not so easy to work with. So sometimes it's very hard to study these perturbations at all. So what I would like to tell you in this talk is how one can use this language I presented and projections to describe basically perturbed topological quantum field theories inside the unperturbed ones. Like, I mean, for instance, in the beginning I told you something about the regular representations or the irreducible representations of finite groups, and they all lie in this simpler representation, and sort of that's the motto of this talk. So now I want to start with some simple, for instance, the free quantum field theory where we know everything about, and do perturbation. And in fact, in the end, I will sort of tell you that all the perturbations of this theory really can be described inside the simpler topological quantum field theory by means of projectors. Okay. Now, I don't want to tell you exactly what I mean by a perturbation because this is very complicated in general. But the only important point is that the perturbations are local. So, and by this I mean the following. So a perturbation is something which takes a correlation function. Let's say you have some space-time surface here. And a perturbation takes this correlation function on this, so a t of this, or let's call it z of this, there's a correlation function, and takes it and changes this to another correlation function. But it does this in a local way, and a local way means that you can restrict your change to sort of parts of your surface. So you can sort of do the following. You just perturb your theory on part of your surface, in here, for instance. What will happen then is the following, that if you do this kind of thing, what will come out in the end is the following situation. You get your, let's say you start with an unperturbed theory, let's call it T0, and perturb it to some theory T, TQFT T here, so the situation you end up with is a correlation function on the whole surface, but now with a defect line inserted here, which separates these two different TQFTs. So this will be a defect line. In fact, these defect lines encode basically everything you want to know about this perturbation. And these kinds of defect lines were introduced by Ilka Brunner and myself a long time ago, and we also did a lot of things with them, so they are very useful to start with. But the one thing which is important here, is they have one important property for what I want to tell you, and that's the following. So let's say we call this defect R, and that's a morphism from the theory T to T naught. Right? I mean, if you look locally in this correlation function, and you had this boundary here, and you only perturbed this on the left, let's say, so you did the perturbation here, then you would get the defect line R. But of course, you can do the same thing in the opposite direction, so you can have a boundary here and perturb it on the other side. So this will be T, this will be T0, or you could do it on the other side, so this will be T0 and this would be T, and this defect line, which is created there, I call R opposite. Yes. So you get two defect lines in this way, R and R opposite. This is a morphism from T0 to T.
R up.
R up, that's right. Thank you. Okay, now there's one important sort of property these local deformations or local perturbations have, and this is the following. So assume that you have part of your surface and you have two boundaries here, and you perturb this thing on the left of them and on the right. Then, as we have seen, there are two interfaces here. One is R and one is R up here. Okay? And then you can ask what happens if I push them close together. Right? So if I push them close together, I basically get a defect in the perturbed theory. So now your theory is perturbed all the way, and I get some kind of defect here. Now, the point about this locality business is that if you perturb in regions which are adjacent to each other, right? I mean, the perturbation, because it's local, is supposed to be a perturbation just on the combination of these domains. So what this means for this picture is that this defect line here should be the invisible defect. So this should be the identity defect in the theory T. Okay? So this means these defects satisfy that R tensor, R opposite, is isomorphic to the identity defect in T. Okay, that's the only property I will use in this talk about these defects. Okay, the only property which is really important here.
So does it have to contain the identity or equal to it?
This has to be isomorphic to the identity. If it only contained the identity, this would mean that this thing which comes out, if you perturb at two adjacent regions and put the regions together, then what you will get out is something which is different from the perturbation on the combined regions. Right? And that's not what we want to have if this perturbation is supposed to be local.
So here are the left and right adjoints of R the same?
The left and right what?
So is R op the same as an adjoint of R?
Yeah, we'll come to this. No, it's not the same, but it's related to one. Okay.
So a local perturbation is an invertible defect or something like this?
A local perturbation? No. Because no, that's not what I said, because I don't say anything about R op tensor R. And R op tensor R will be not invertible. So I only say something about one direction. So the way to think about this, look at renormalization group flows, right? You start with some big quantum field theory and you do some non-trivial RG flow to something smaller, right? And then it's clear that this renormalization group defect from the bigger to the smaller can't be invertible because the smaller just doesn't have more, doesn't contain as much information. Exactly, so they're not invertible. Yeah, that's very important. They're not, in general, invertible.
Right inverse, but not a left inverse.
Exactly. Okay. All right. So what this means basically is the following. So now I want to tell you how this looks in string diagrams. So you have the string diagram like this. There is R, and there is R opposite, and there is some map phi here. So this is a map from R tensor R op to the identity of T, and you have the inverse of this, which is this R op, and let's call this capital psi. So this is a map from identity of T to R tensor R op. Okay? You have these maps, and they are inverse to each other, so phi is equal to psi inverse. Okay, that means you can do the following thing. You can concatenate this thing, for instance, in this way. You can start with R tensor R up, here go down, and then have here R goes to R up, and you have your phi here and psi here. And what this means, that they are just isomorphics, so this means that this is the same as this. Okay. So that's one thing, and the more important thing is the other direction. So you can also have this direction where this is phi. And this is psi. In the other direction, you have phi here and psi here, so you compose them in this order. And since these are invertible, this just means that this is the invisible defect. So that means whenever you see a loop like this, so again, here's R and here's R opposite, whenever you see a loop, you can just take it away. Okay. So one thing I want to do is the following. So you ask about the relation to the adjoints. So one thing I want to do is the following. I want to take this phi and push it along the circle down here. So this I can do, and what I get is the following. So by pushing this around, I create an R right dagger here. And so I get a loop which looks like this. Here's R right dagger, and here is now some kind of other morphism. I call it phi, which goes from the identity to R tensor R right dagger, and this map here is just the evaluation map. Okay, nothing happened. I just pushed this morphism down here. Okay, and this again is the identity. Okay, and this loop I will now use a lot. So I now, in the following, I will forget about the R opposite. I just use the R right dagger instead. Okay, now I want to realize the perturbed theory inside of the unperturbed theory. Realizing theory T inside T naught. How do I do this? Well, I start with a correlation function, and the correlation function was just Z of, well, I start with some surface. Let's make it a sphere or something. And there might be some insertions of local operators or some defect lines, whatever you have here. And this is supposed to be, in theory, T naught. So theory T naught was always blue, so I make it blue. And now I use these kind of bubbles here. So this was a bubble which had the blue theory on the outside, And this bubble was nothing but the identity defect. So what I can do in this correlation function, without changing the correlation function, just inserting these kinds of bubbles. So I could put a bubble here, for instance, like this. So there's this dot, which corresponds to this phi. And inside here is theory T. And I can put several of them without changing this correlation function. Okay? Now I just use conformal topological invariance. So this means I can just expand these islands. Now I have islands of T in this correlation function, and I expand them. Expand them, and in the end, I'll end up with the following correlation function. So it's a correlation function there again. There were these local operators inserted, and now what I get in the end is some kind of ribbon graph on here. Outside of this ribbon, I have theory T now, and inside of this ribbon, I have theory. This was T naught. And inside, so my theory T is now somehow contained in this ribbon. Okay? So I did this without changing the correlation function. So now I can sort of push it to the end and just put these defects together, right? And this means that the correlation function in the end looks like this. That's a correlation function which is now purely in theory T naught, but now it has some network of defects in there. So what have I told you? I've told you that a correlation function in this perturbed theory can be realized by looking at correlation function of the unperturbed theory where just put some kind of network of defects inside.
So on the left, it should be T naught inside these bubbles.
No, T naught is on T naught. Yeah, right. Sorry. Yeah, T naught is the theory we start with. Simple free maybe theory which we should start with. Okay, so now that's cool because if you have a free theory, then you know everything about it, including correlation functions with defect. But if you have a complicated perturbed theory, you typically don't know very much about it. So you have sort of rephrased complicated correlation function in terms of something extremely simple. Now I have to tell you what the network of these defects, how this looks like. So the network of defects is built out of the following things. For one, there's a defect P, which is nothing but R right dagger tensor R. And this is in course more of T0 because this comes just about, so look at this, so you have defect R dagger here and R there, you just squish them together to get this line defect here, right? So the defect is built out of this defect here and all its adjoints. So P dagger I, so I take I times the right adjoint, or you can take J times the left adjoint of this. So the network is built out of these kind of defect lines. Now these defect lines are very special. For instance, this defect line here is an idempotent. So because if you take P tensor P, then you just look at the definition. This was nothing but R tensor R right adjoint times R right adjoint times R. Now the composition of one morphisms is of course associative. So you can just look at this here, and this is just the identity, the invisible defect in the theory T. So this here is nothing but R dagger tensor R, which is nothing but P. Okay, so you get.
I'm confused about one aspect of this. So you were doing operator insertions at points, and now those points are in the middle of your red segments.
Yes. Mm-hmm.
So the defect won't be purely built out of R dagger, right? Because you've got to do something with the operator insertion.
Exactly. So you're right. So the operator insertion lives here. I'll come to this in a minute, how you encode things. But these will just be some operators which now live on the defect. So they are in the defect spectrum of this defect, which is something which is purely in the defect theory of this theory. So you're right. Even, I mean, for instance, you could also have some defects or boundaries here, and they would sort of translate into something in this theory T naught. Which are then can be purely described inside of T naught. So you don't have to sort of go through this theory T to get them. Okay, but I'll come to this later. So P has this nice property that it's an idempotent, so it's a projector or a categorification of a projector. So that's one. Now for these networks, you also need junctions. So these P's have junctions. Now how do they look like? Well, they look like something like this. Right, where now you have here R dagger, R dagger, R. And this translates into junction like this, or P, P. And of course, this here gives you an associative algebra. Namely, this kind of junction satisfies like this. The same as this, and this is obvious when you draw it in this form, right? Because you have topological invariance, you can move your things on the ribbons around. So this is an associative algebra, and it also has a unit. What's the unit of this algebra? Well, it's basically just the co-evaluation map R dagger. Okay, if you put this onto one end here, you can close it up, and then you can use this move which I had on the right blackboard here, which defined the adjoint basically, and to pull this thing up to get just R. Okay, so that's a unit. So it's a unital associative algebra, and it also has a co-algebra structure. So what's the co-algebra? Well, it's basically the same thing. So you have R dagger R here, and you have, again, R and R dagger. But now here you have to have this funny homomorphism phi inserted, okay? Which comes from these bubbles. You recall there was this bubble with the two isomorphisms, and you pulled one on top to get the evaluation on top. So here you really have the evaluation map. But on the downward things, you only have you have this morphisms phi. Okay, so this gives you a co-algebra structure. And again, this co-algebra structure is associative for the same reasons. Before, if you look at this in the ribbons, you can sort of deform all the ribbons as you like, and you get the co-associativity. What this algebra doesn't, or this co-algebra doesn't have, is a co-unit. Why doesn't it have a co-unit? Because for a co-unit, you would have to be able to close this off in a way which is compatible with this adjoint moves, but there's no cap here, right? I mean, here is defect R, and here is defect R right adjoint. So if you would close this up here, then you would have to have some R right adjoint here, but there's just an R here. So you can't close it off. Okay, so in general, there's no co-unit. Okay, and there are some more properties. For instance, it's a Frobenius algebra. So this means that this is the same as this is the same as this. Okay, and it's also separable, which means that this is the same as this. So this again something which is obvious to see, because here inside, if you draw it as ribbons, then the thing inside here is just the bubble which was 1. Right? So you can just take it away. Okay, so it's a separable Frobenius algebra, and it has another property which we call the projection property, which is this. also follows easily from the representations in terms of these ribbons. So now what I've shown you is how one gets to this network of these defects P and all their adjoints, and this defect P has some very nice structure here, and actually this structure carries over to all the adjoints. So all the adjoints have similar structures, where now if you take an odd number of adjoints, this won't have a unit, but it will have a co-unit. So unit and co-unit get exchanged when you sort of do the adjoint operation once. Okay, but apart from this, the structure is the same. Okay. So now, as I said, so you start from your theory T0 and can basically construct correlation functions in your theory T by inserting some network of these interfaces or of these defect lines P in this correlation function in the simpler theory T0. And now, how do you do this? I mean, is there one way to put the network? Well, of course, as you've seen, we just started with these bubbles and expanded them, and we can expand it how we like. So there are different realizations in terms of different networks, but they are all the same. And the way to relate the different networks, which are all the same, is by means of these local moves here. So you use these algebra, associativity, co-associativity, Frobenius property, the separability, and so on. So you can locally change your networks and still get the same correlation function.
You don't literally mean the algebra here, right? There's no vector space around.
Well, there will be a vector space around, yeah. This will be the vector space of fields on this thing. It's an object, yeah.
Yeah, so it looks like what people call an algebra object.
Yeah, it's an object in this category, yeah. Mm-hmm. I would rather like to sort of consider it a two-category instead of a tensor category, but well. Okay. Okay. Now, as I promised, all the information about your theory T is now contained in this defect T, in this defect P, in this idempotent defect.
Have you shown how you reconstruct the interactions in this theory T from P?
Yeah, I will tell you how to do this. So all information can be reconstructed from T. So for instance, one important thing about this theory is the bulk spectrum. Of theory T. Okay, how can I get this? Well, I get this by means of the following. So the bulk spectrum of your theory T is nothing but the homomorphisms of the identity defect in T to itself. And this is isomorphic to the homomorphisms of the defect P to the identity defects in T0, which is isomorphic to the homomorphisms of P to P. Okay, so you can get this space of morphisms from this space of morphisms. So what I tell you is that the bulk fields living in this more complicated perturbed theories are nothing but the defect fields which sort of live on this projection defect. So how does the isomorphism here look like? Well, I told you that a space like this is related to these circles where you now have two insertions of the identity defect. Maybe I draw it a little bit bigger. Okay, and so you start with the identity here and with the identity here. So this space which your TQFT functor associates to this interval is nothing but this space. And I now sort of draw you the map from here to there. And the map goes as follows. So you just take your defect here So you split the identity up into P tensor P right adjoint. Okay? And then you do something like this. Okay, so you have your P right adjoint here, and there's P there, and P right adjoint tensor P is actually nothing but P in this context. Okay, yeah. Okay, and this is the isomorphism which goes from hom it t to hom p it t, because you can sort of put in another identity defect here without changing anything. And this homomorphism here just means that you start with your defect P here and split it up in P tensor P here. And you maybe put in another identity here. Okay, you go from this to this space. Okay, so that's an isomorphism just because you can sort of draw everything around, juggle everything around. So this, let's put it in here. All right, so that's an isomorphism. So you now see how to reconstruct the bulk spectrum. What about the bulk, so the algebra of bulk fields? Well, the algebra structure is just a functor Z associated to a pair of pens like this. And now this was a pair of pens which was in the perturbed theory. But now what we do is, again, we put in these bubbles and sort of these islands of theory T and expand them, and what we'll end up with is this correlation function in theory T naught now. So this was theory T. Okay? So you see that your algebra structure on this space, so I now wrote it in terms of this space here, which sits here and here, is nothing but the algebra of your theory T naught with this defect inserted. Okay, in this way, you reconstruct, for instance, the Frobenius algebra corresponding to the TQFT, to the bulk TQFT. But you can go on and think about what are the defects in the theory in T, expressed in terms of theory T naught, okay, or defects in theory T naught. Now, what you do there is the following: you start with a defect between, let's say, the perturbed theory T, that's T, and some other theory which we call T prime. Okay, that's some other theory, and we have a defect in here. Let's call it defect D. Okay, so that's in the morphism of T and T prime. Now, what happens to such a thing in a correlation function when you do this trick with expanding the bubbles? What happens to this is the following. Well, you just tensor this defect with an R dagger. So what you'll get here is defect. Here's again T prime. Now here's theory T naught. And this thing will go to R dagger tensor D. Okay, just if you inflate your bubbles, you get this defect tensored with this. And this is now a defect in more of T0 T prime. Okay, out of a defect here, I can get the defect here. But of course, I can sort of do the other way around by just multiplying by R. So if I tensor this defect by R tensor R dagger is the identity, I get back this. So this is a one-to-one map on the image. So whenever I have something which is in the image of the left multiplication by R dagger, there's a one-to-one map back and forth. Okay? So this means that my defects in this theory T naught, which correspond to defects in the theory T, are exactly those defects. So defects in more T naught T prime corresponding to defects in more T prime are exactly are the defects D in more T naught T prime for which the following holds, namely P tensor D is isomorphic. So D. Okay? These are exactly the defects in the image of the left multiplication by R. Okay, so now you now have a nice characterization of your defects in the theory T naught in terms of the defects in the sort of simpler theory, your defects in the theory T, in terms of your simpler defects in the theory T naught. Okay. And the same works for defects where the sides are somehow switched.
But it doesn't really tell you how to find them, right?
Well, you just go through all the defects. If you have a P, you go through all the defects and check if P times D is D.
If you have projectors, you can do it.
If you have projectors. And I told you how to get them from the perturbation. Right? So whenever you have a perturbation, you get this R's, so this perturbation defects, and with them you get the projectors. But now, of course, the interesting question is to turn this around, right? Now you want to start with your simple theory T naught and try to find all possible local deformations by just looking at the projectors. So that's actually the next point. So turning this around.
That sounds hard.
No, it's much easier.
Okay.
It's much easier because
this already sounds hard. I don't see why this would be easy in general. To solve this equation P tensor D is...
Well, it depends how complicated your categories are.
I mean, of course, I can always construct a solution by just tensoring with P, right? Because P squared is equal to P.
Yeah, I'll come to this. Yeah.
So I take any morphism in T naught, T prime, and then...
Yes. Well, if you have one, you can. But I mean, if you have some, you see, if you have a prescription of these categories, you can do it. You can find it, right? I mean, you have to compare it with working with defects in a category which you can't even describe. This sort of defect category associated to T. Well, T can be a very complicated theory you don't know anything about. Whereas the theory T naught is the free theory. You know everything. It's sort of, for instance, you can describe this if theory T naught is some free Landau-Ginzburg theory. It's just matrix factorizations of 0, right? And you know everything about that, right? It's, you can really work very explicitly with this, whereas in the more complicated situation in the theory T, you might not even know where to start. So you have to compare this. Of course, it can be hard, but so turning this around, what we now want to do is start with a theory. Let's say T naught, and find a projector. Let's call it P in more of T naught, T naught. Okay, if you have a projector like this, then this projector, so projector means P tensor P, isomorphic to P, and out of this, all these nice relations follow, that it's a Frobenius algebra, that it's separable, that it has a unit, and so on. All these nice local properties follow, and so by means of putting nets of this defect in your theory T naught, you get another 2D TQFT. So by means of putting P networks into theory T naught, you get another theory 2D TQFT T. Okay? We don't know what it is. It's just there is another TQFT T which you can obtain in this way. And now comes sort of the punchline. And the punchline is that whatever your defect P is, this defect always splits up as a tensor product of R dagger times R. So this means that this defect P always comes from local perturbations we started with. So that's the fact. And the fact is that for such a P, there exist R in more of T, comma T0 with P is isomorphic to R dagger tensor R. Okay, and this and R tensor R dagger is just the identity, the invisible defect in theory T naught, in theory T. Sorry. Okay, so this means that whenever you don't have to think about anything, you just need this projection property, this idempotence, and whenever you have this P is made out of sort of this back and forth defects, so it really comes from a local perturbation which we started from. So now let me just give you an idea why this is so. So why? So the reason is P tensor P is isomorphic to P. This means we can understand P as a defect. So P can be realized or does realizes a defect in more of T naught. Right? That was one condition. So the defects in the simple theory, which had the property that P times these defects were P's, were already could be used to describe defects in this theory. And since this works from both sides, what is also true, and this defect I call R, and indeed R dagger, which is now in more of T0T, is also realized by P itself. So P now takes over the roles of R and R dagger in the same way. So just make a picture. So if you take now R and R dagger, what this corresponds to, right? We wanted to describe our theory in between. This was the theory T by these P networks. This is nothing else as putting a P here and then some funny P network in between P. So this is now the P network. And the rules of your P networks, which allow you to basically deform your network away, is that if you squash this together, this is nothing but P, because P tensor P is P. So you see that if you take this R and tensor it with R dagger, you get out P. Now what about the other side? So what we also wanted to know is R times R dagger is the identity. And well, that now looks like this, R times R dagger. This corresponds, by means of this corresponds to the following situation. So now you have your P network on the outside, so you have P here, your P network outside, and you put this together, so this is nothing like this, okay? But this just adds another line to the network, and you're allowed to do this without changing anything. So this is just the identity on the theory T. Okay? So the punchline is that whenever you have such a projector, it really comes from a local perturbation of this sort. And you can reconstruct your theory out of this projector itself. So now I want to mention that if this somehow looks a little bit familiar, that's because it's very closely related to the so-called generalized orbifold constructor. Generalized orbifold construction. By Fröhlich, Fuchs, Runke, and Schweigert, and which has sort of been adapted to this two-category setup by Kragwil and Runke. Okay? The difference here is that they assume, so they didn't sort of need this idempotence P. What they had to assume instead is something like the fact that A left adjoint is the same as A right adjoint, or P I should call it. So they usually assume pivotality, and this was very important for their construction, and we don't need this. So in a sense, what we do is some kind of generalization of a generalized orbifold here. Okay, so that's the general picture. Now I want to briefly mention the examples where we can really do everything explicitly.
Sorry, can you say 2 more words about this? What is possible in their case? When P left adjoint is P right adjoint, then you said something about this co-unit? So
exactly, so they assume some more. So they have to have a unit and a co-unit. It's separable Frobenius. I mean, they use a separable Frobenius algebra, which is also symmetric and has a unit and a co-unit.
So then this R is invertible in that case?
No, I don't think so. They just need the fact that R dagger is the same as R, or is isomorphic to R. Because and then they can use this unit property.
Somehow. So this is not an RG flow then? How should I think about this?
Yeah, that's right. So in this case, you can't describe these RG flows in this way. That's right. I'm not so sure, actually. The point is that in our examples, which we look at, we never have this situation. This might be possible that you have some kind of projection in a pivotal theory like this, where you can play the same games, but I don't know. So the situation which we studied and where you have a real nice renormalization group flow, they are all non-pivotal. So we can't use their construction. So it's much more complicated. So for instance,
I'm asking whether their construction actually has the property that this defect R is actually invertible.
No, not true. That's what they often do. That's what they use in, when they describe what they call orbifold equivalences. That means that there's an orbifold construction which you can make in both directions. So you can go back and forward. But they describe more general situations as well. So for them also this R does not have to be invertible in general. Okay, yeah?
It would seem that it would be natural to think of perturbing the theory as modeled by something involving a cobordism from one surface to another.
Okay.
Does this fit into a cobordism theory of the surfaces itself? That would take the category up one level.
Yeah, I don't know. I haven't thought about this in this way. So possibly, yeah. But I haven't thought about this. But it's interesting. I mean, in principle, you can also play this game in higher dimensions, right? I use 2 dimensions just because it's easier to draw on the board. But, I mean, you can do it with 3D TQFTs as well. Now, the defect lines become sort of defect surfaces, and you can play the same game. So it would be very interesting to find nice examples about this, where you can study this. But I don't know.
But this is a continuous deformation, for example, no?
Yeah, you can do it with continuous deformation.
I mean, what Lou is describing would be a continuous deformation.
Yeah, you can also
describe. For example, this orbifold story is not continuous.
Exactly. So the example, so the continuous deformations are in a certain sense boring, because if you have a continuous parameter, nothing much changes to your stuff. I mean, everything is invertible. I mean, you can still do it. You can describe a sort of deformed theory inside your theory and so on. But then sort of the very nice point, or the point which I want to make here, is that you can really describe very different theories. So you have a continuous deformation, then your theories are basically isomorphic to each other. So there's not much change there. But the perturbations which I would describe now, are much more complicated in that you really lose information there, and your theories get more complicated. So
the space of defects necessarily has codimension 1.
Exactly. So these kinds of defects are always codimensional 1 walls in your theory.
Then maybe it splits the space of all deformations into chambers, and one chamber has the same topological type.
Possibly,
and to go from one to another, you have to go through essential deformations.
Exactly. Yeah, true. I mean, there are all sorts of these kind of games you can play with these defects. It's true. Yeah. Okay, so let's come to the example.
We can have one more question.
Yeah, sure.
Can you have 2 such projections which are orthogonal
Yeah, that's a very good question. So we haven't studied this, but in principle, what I would suggest is if you have a projection P, then you can take a cone of P to the identity, and this should be the one which is orthogonal. But we haven't really done very much with it. But it's true. I mean, that's something which should work.
So this would be another projector, you say?
Yeah, I think so. As I said, I haven't worked out the details, but I think it's true.
And the resulting theories, they have what property? There are no defects between them, or what is that?
Well, I think let's discuss this example, and then I can answer that question. Okay, so the example is the Landau-Ginzburg model with one chiral superfield. One chiral superfield. Let's call it X. And superpotential W equals X to the D. Okay? So the ring, sort of the bulk ring, is just the Jacobi ring of the superpotential. And you can now perturb this by adding some lower order monomials. So you can do something like lambda x to the d prime, where now d prime is smaller than d. And then you have a renormalization group flow, and the renormalization group flow in this perturbation will drive this constant here to infinity in the infrared. So in the infrared, so if you follow this renormalization group flow until the end, you get to x to the d prime. So a theory with w equal x to d prime. So this here will be your theory T naught, and this here will be your theory T. Okay? And for this case, a long time ago with Ilka-Brunner, we worked out the defects which correspond to these R's. Okay? And the way we did it was because these perturbations are, in a certain sense, complex structure deformations, so the defects which connects these two theories should be of A-type. And A-type, so A-type supersymmetric defects, haven't been studied very well. So we went to the mirror of this, mirror symmetry. And the mirror symmetry, so the mirror of this model is just an orbifold. That's the orbifold of this Landau-Ginzburg model by a ZD group. And here, of course, you have the Landau-Ginzburg model W equals to xd prime modulo Z prime. And now this perturbation is of Kähler type. So that's Kähler type. So this deformation on the mirror should be described by a B-type defect, and these are matrix factorization. And these are sort of equivariant ZD cross ZD prime equivariant matrix factorizations of x to the d minus y to the d prime. Okay? So in terms of these matrix factorization, we could somehow identify the defects R in this theory. And from there, of course, one can look at what are the defects P. So we can describe what the defects P are very explicitly. And in particular, we obtain the theory T, so obtain the theory W is equal x to the d prime modulo Z d prime inside the theory W is equal to x to the d modulo Z d for every d prime smaller than d. Okay? Now you can say, okay, so far, well, these models are basically sort of, I mean, if you know how to deal with this model, then you also know how to deal with this model. So this doesn't make much, I mean, you don't make much progress by describing this model inside this bigger, slightly bigger one. So what one can do is take the limit of d goes to infinity. Okay, if you take the limit of d goes to infinity, this model here basically becomes a free field. Okay, a twisted chiral field. Okay, that's the most simple theory you can write down. Okay, and now what we say is, by looking at projection defects in this free chiral field theory, you can describe all your minimal models. Okay, all models x to the d modulo zt can be obtained inside the model the free chiral field or twisted chiral. Doesn't really matter. Okay? So, and that's of course progress. Now you can sort of and you can not also describe these single models, but you can also describe the flows of these models by means of flows on the defects, on these defect networks. So you can describe all these things in a very nice way.
What happens to the orbifold and the d goes to infinity limit?
Yeah, it stays there. So this just means that it's not a free chiral field, but a twisted chiral field. So you can describe this by as an orbifold formally z modulo z. It's a u1, yeah. Maybe I should say z modulo u1. Actually, so it's a theory. It's basically something like a u1 gauge theory of a free chiral field. Okay. But it's very simple. You can describe it in terms of polynomials. It's very easy. Okay, so this brings me somehow back to the beginning. At the beginning, I said, well, you can, in representation theory, describe all the complicated representation of finite groups by looking at a very simple representation, namely the regular representation, which you understand very well, and looking at projectors there. And now, in this example, you see that you can see a whole bunch of very sort of slightly complicated topological quantum field theories inside a very simple quantum field theory, namely the free quantum field theory. So it's a very powerful tool to study things, and actually there are some sort of future things one should look at, and which we haven't had the time to do. For instance, you can look at deformations or perturbations of the theory in terms of perturbations of this projection defect. So you could, if you look at a perturbation, you start with your theory and now use as your P just the invisible defect. Then sort of inserting these networks doesn't change the theory. And now you can do a deformation or perturbation of these defects, right? And this should describe your perturbation of the whole theory, right? So you can basically localize your perturbations, your bulk perturbations, which are perturbations of a two-dimensional thing, to perturbations on one dimension less, which is sort of very, very nice because perturbations are complicated, but the lower the dimension, the easier they are to deal with. And of course, the other thing, well, and in this spirit, you could ask, well, look at things like TT star equations. I mean, you can reformulate this in terms of these defect categories, or and this might also be a nice additional viewpoint on them. And, well, I mean, the other thing which I mentioned before is that actually I think this should hold for any dimensions, not only for two. So you should be able to play these games in any sort of d-dimensional TQFT, and it would be very nice to have examples. So I don't know very much about higher dimensional TQFTs, but if any of you has a nice example where one could sort of work these kind of things out, then I would be very happy to hear about it. Okay, that's it. Thank you.
Are there any questions?
Okay, can you say anything about, do you learn anything from this about the space of theories?
Yeah, you could. Well, in this case, everything is understood. That's why we use this example, right? We knew everything beforehand. But in principle, yes. I mean, the idea is that now instead of studying, deformations of bulk theories, you can just look at the category of endo defects of your theory, and then everything should be contained in there. And it's, of course, a much simpler thing to study well, at least in some situations. It's much simpler to study that.
And prediction that in 3D you will need spin structure, and in 4D you will need spin C. Your cobordism will possibly.
Yeah, I mean, the more you put into it, I mean, of course, there are sort of, you can incorporate more and more structure, but still, I mean, it should still work out. I mean, I don't see any obstacles. You can enrich this to every level you need, and it still should work. I mean, there's nothing. I mean, this is all very general. I mean, the only thing you have to know basically is this locality of the deformations, and once you know about this locality, everything follows, and that's the beautiful part of it, right? I mean, from locality, all this story basically follows.
In cohomological TQFTs, perturbations are sometimes described in terms of Moore-Cartan equations.
Yes.
How that relates to your projectors?
No, I don't, but I mean, it should be possible to describe this in terms of something related to these defects, P, or basically the identity defect. So if you start at a theory, at a theory T, then everything you do with this Moiré-Cartan equation or whatever, or TT star, should be related to spectrum on your identity defect of your theory, and you should be able to describe everything in terms of this defect category. But I mean, we haven't really worked out any example of this, or it's not clear how useful this is really. What I think is quite useful is that you might be able to find, by just looking at this endo defects, you might be able to find all the possible endpoints of renormalization group flows without really thinking about anything, right? By just, identifying all the possible projectors. So if you start from there, you don't need to do very much. If the category is simple, then you can work this out.
Other questions? Let's thank Daniel again.